welcome everyone to zkWarsaw Meetup 14. It's so cool to see you here in the very spot where we had our very first meetup this year. Today I have one announcement that I made last time already, which is a big thank you to our two new sponsors, Ethereum Foundation, ESP and Gilea. And the other announcement would be that tonight we will have a big chunk of maths brought to us by Bartek on the topic of STARKS, and then we will be heading to have some drinks over at the upper deck in approximately 1 hour. Until then, Bartek is happy to have interactions and to resolve questions and lacks of clarity as we go. So feel free to use that opportunity. Now please give it up to Bartek.
So hi, I am Bartek and I am engineer in the zk space for quite some time now. And what I want to explain you today is how the zk protocol achieves its scalability. How is it even possible, and we need to intuitively understand that to really use the technology the way we should. So today's talk is about ensuring computational integrity with polynomial constraints, and because in the zk space we've got a prover and verifier. And verifier is really skeptical about prover's statements, and what the prover needs to do is prove to the verifier the computational integrity of the program he ran before. And when the prover supplies this kind of proof, whatever it is, we will see in a minute, the verifier is convinced about the results of the program the prover calculated, and the verifier can use these results as they were truly true, not like checking them again, recalculating the program again to make sure that these results are really correct. So that's the core stuff, because when we have a tool to ensure somebody, to prove to somebody computational integrity of the program we ran some time ago, we can achieve the scalability of the zk. So that's a core statement here. So overview of this lecture is that we are gonna start with the polynomials recap. Why do we use polynomials everywhere? Because that's can be kind of bugging. Also the essential primitives, and after that, the point 2 and 3 is gonna happen on that whiteboard, because we are gonna explore what is the let's say the Fibonacci trace. I will explain what the trace is, but we will explore the Fibonacci program, calculating the 8th Fibonacci number, and we are gonna explore. We are gonna develop the way to prove the computational integrity of this calculation to some external party. We are gonna have a close up on it, and we're gonna when we do this, we're gonna explore what boundary constraints and transition constraints are, and all of the stuff in between. And the last part is gonna be point 4, the idea of provable CPU architecture, and because nobody have any interest in calculating the Fibonacci numbers, that's just an example, but we need to have an idea of how to scale this sort of thinking to have a generic provable CPU, right? Because that's what we are interested about. Okay, so polynomials motivation. Why do we use polynomials everywhere? Yeah, so the polynomials have a nice defined arithmetic. That's kind of simple. We can add, multiply, divide, subtract them. That's kind of obvious. But in the polynomial space, there exists really lots of really powerful tools. like error correction codes, so Ritz-Solomon codes, and they are especially useful in the Fry protocol. Later we will explain what this is. But lots of good tools in the polynomial space. Also, the polynomials experience something called proximity gap, and the proximity gap of polynomials can be explained with the simple example that we've got two completely arbitrary examples of polynomials, and what we can see here is that those polynomials cross in 2 points only, and so the proximity gap is something like this. When you've got two polynomials, the amount of points that they're gonna cross each other is finite. It's not infinite number. It's just some number 2, 3 or something, or like 1,000, but it's finite. But the number of the points that this polynomial can be evaluated on is infinite, because it's the whole x, like let's say axis. So like when you've got two polynomials, either almost none of the points on the x-axis are gonna be the same between for these two polynomials, or either all of the points are gonna be the same for these two polynomials, because they are gonna be necessarily then the same polynomials. So you don't have like polynomial that has, let's say, 50% of the points the same between two of them, or like 10% or like 1%. It's gonna be value that comes down to 0, probability of finding random x that is gonna be the same value between two polynomials is gonna be like 0 when these polynomials are different, and 100% when these polynomials are the same. So this is the proximity gap. We don't have like similar polynomials with the 50% of the points. We've got either the same points on the whole x-axis, or almost none of the points on the x-axis when you randomly pick a random point on x. So that's really important stuff, because in the zk protocol, the verifier is gonna just like choose a random value and check properties on the polynomial, and the probability that it's gonna find some special value that is like, and when it's like prompting a couple of times, probability of finding like, for the malicious prover, for the malicious prover to like pass this sort of test is gonna be like negligible and like totally not in the scope. So that's a proximity gap. Either polynomials are the same and every point is the same, or are they almost none of the point is the same on two arbitrary polynomials. The first, so that's yeah.
So the proximity gap is the same as the Schwarz-Zippel lemma. That's the same. I
don't know. I don't know what this lemma says, but you can read more about this stuff when you read the papers about Fry protocol, and there is like a proximity gap research, and probably this sort of lemmas are used there, but I can't say right now.
Basically, it's the number of points the polynomials agree on.
Yes, exactly.
So that's the same, I think.
Yeah. Okay, that's cool.
The other question.
Yeah.
Ritz-Solomon codes.
Yeah.
You say the codes is a reason for the polynomial motivation.
No. Yes.
Yeah. But they are also used in CDs. Like those CDs
yes.
Polynomials. Or is
yes, exactly. This is the error correction of like when you read from the CD. You can have like some interference in the laser when it's like reading the light, and some bit is gonna flip, or something, and you have to like retrieve the data that was really there on the CD, and this is the error correction. And the error.
Polynomials as well.
Yeah.
The data availability something the same.
Yeah. So pretty much every like transmission, also radio transmissions that have to be like legit, and we can like count on them. They have to go through some error correction, because you're always gonna get some correction, some errors in the transmission lines. Yeah, but this is not. It's well engineered, but it's some overhead, of course. The fastest way is just to send and receive, but with the error correction codes, it's slightly heavier. Okay. So the first primitive, or like definition, or like whatever, is the execution trace. And the execution trace is some, let's say, vector or table or some structure that has the every state of the system encoded into that. So in case of Fibonacci trace, we're going to have just the value of the Fibonacci, but the trace is just the every system state encoded into the, let's say, table, and the important stuff is that this trace needs to follow certain rules. So it's not like random, but this trace needs to have a rule. For example, like some of fields add up to the field below, and that's it. So this trace like has to undergo or has to like respect some certain rules. We are gonna explore what these rules can be and stuff. Okay, next is the Fry protocol briefly. So Fry protocol is the algorithm to so the output of the Fry protocol is some sort of proof that can be verified by some party, and this proof is gonna pass only if this function h of x is a polynomial of low degree. So it's like a checking, let's say, valve, or let's say checking function, that if I put h of x, some function, I don't know what this is, but h of x I put into the Fry, and this Fry is going to output me the proof always. And when this proof verifies on some third party, I know that h of x was polynomial of low degree. The low degree polynomial is kind of like not like strictly defined. The low degreeness of polynomial we define, so it's like the parameter between prover and verifier. So when, let's say, we can like say it's okay, it's 10, or like it's 100, whatever it is, it's some definition here.
In practice, what are the typical numbers?
In practice, the low degree polynomial is the length of the trace, if I'm not mistaken. So it depends on the size of the polynomial of the program and its number of steps. So it's pretty big. Yeah. It's pretty large in the practical examples.
But it has to be low degree with respect to.
Yes, with respect to whatever parameter we say. So it has to be under that, or like exactly the same. And when this polynomial is not of low degree, the Fry protocol proof is not going to be very successfully verified on the verifier side. So this sort of primitive that we have is going to make sense a lot when we will gonna explore the mathematics, because it's a let's say useful primitive to have to just check if the h of x is low degree or not. Yeah. So right now the equal or lower. Yeah? So that's it. It can be like trivial polynomial, it's gonna pass. When we've got like polynomial x minus 1, it's gonna pass also. So that's it. Okay, so any questions so far? I think.
So we treat Fry as a black box.
Yes, we treat Fry as a something that we have. It's like previously developed, and we can like explore this maybe on the next lecture or something. But
maybe you just want to use the chess over there.
I sit all day, but others can sit.
okay.
What does Fry stand for?
So it's a fast read Solomon. So fast read Solomon interactive oracle proof of proximity. So this stuff proves you if the polynomial h of x we send is close to the low degree polynomial. So it's not a algorithm that is it's a probabilistic algorithm. It's really high probability that if h of x is a high degree, it's not gonna pass. So it's really high probability for that if you got a.
So we're just proving that, not that and something else.
Yes,
We're
once
just
again.
proving the low degree
Yeah.
of polynomial,
Yeah.
not.
Yeah, nothing else.
specific polynomial or
Yeah, nothing else.
committed polynomial.
It's like a Boolean value. It's correct or not, but it's gonna emerge on the verifier side. Okay. So the first thing, like I said, we start is the Fibonacci step-by-step walkthrough. So the first we're gonna start with the execution trace of the Fibonacci program, And the execution trace of the Fibonacci program is exactly as it is here. So it is every state of the machine that was calculating the Fibonacci program. So we started with the 2 ones because that's how we define the Fibonacci, and it started with unity, second unity, and later it's calculating 2, it's calculating 3, 5, 8, and it's calculating 13 and 21. Yeah, so that's the execution trace of the Fibonacci. And right now, we want to develop the mathematics tool that is going to prove this and ensure this computational integrity of this kind of trace. So we need to define the rules that this trace is following. Yeah.
Sorry, what exactly does it mean, integrity?
Yeah, exactly. So we mean by integrity that we define some rules that this trace needs to follow. And when we prove to somebody the integrity of this trace, we've proven that every rule we defined was followed or was like met by this trace. So that's it. That's the
mathematical formula.
Yeah, the set of rules can be like, yeah, this is like the relations, right? This is the rule is gonna be just a relation between like trace cells, right? So let's move this information to the polynomial space right now. And if we want to move this information about these values to the polynomials, we need to interpolate a polynomial on that. And to do this, let's say those are our AIs, AI, so A1, A2, A3, A3, and up to A8. And the polynomial is going to be called a trace polynomial, and it's going to be of the formula that we've got Txi is going to be equal to AI. So that's just going to hold the information about this trace. And the AI values are obvious because those are those, but we have freedom about these xi's. We can like have this 1, 2, 3 up to 8, but it's gonna be like later difficult for us. We can like get a little bit clever, and because we do the interpolation here, and we know that there exists like algorithm that is called fast Fourier transform. And if we want to have this interpolation faster, we want to have a FFT-friendly domain here. So xi needs to be FFT-friendly domain. And this FFT-friendly domain, the definition of the FFT-friendly domain for this interpolation is going to be that, let's say we're going to call this Q. And this Q to the 8th power is going to be 1. So it's going to be the 8th root of unity. So for this xi's, we're going to supply a Q0, Q1, Q2, Q3, and that's going to go for all the AI's. So we can like write this, that TQI is going to be equal to I is going to be equal to AI. So that's going to be the definition of our trace polynomial. Any questions so far?
Just a reminder, what's with the unity?
Yeah, in Polish. Jakby tak jakby chodzi o to, że nawet nie wiem jak to po polsku dobrze powiedzieć, że mamy jakąś wartość Q, ale Q do 8 jest równe 1. I to Q ma jakąś wartość. I tyle. Yeah, and the important, the definition of the 8th root of unity is just this formula. That's it. I don't know what this Q is. It depends on the fields, whatever we think, whatever the necessity is. So we've got a trace polynomial right now.
But there is any connection between Q and, let's say in that case, Fibonacci sequence?
Not really. This Q is just some x that we can define x as like the row number of this, right? We can define the x as 1 to 3 up to 8, but we define x in this way So the interpolation of this t of x is going to be efficient. That's the only reason here. Yeah?
Connection between Q and 8, not Q and Fibonacci numbers, but the fact that we've chosen to talk about 8 Fibonacci numbers. That's the
Yeah. Because this,
8 is important.
yes, the 8 is important because this is the length of the, this is the length of this trace. If this number here needs to be the power of 2. So if we had trace 9, length of 9, we need to top up this to the 16, and that's going to be a little bit wasteful. But yeah, that's why I chose 8, because it's...
So 8 could be some kind of jak bardzo dopasowany jest ten polinomial, tak?
No, the Q is just, let's say, the identifier of the place. Yeah, so it's gonna be like the first value in the trace.
Consider the constant.
Yeah,
So
it's gonna be
from 1 to
Q0.
3, you have
This is gonna be
2 to the
Q1.
power of 2
Yeah.
to the power of 3. And,
And this is xi's and this is ai's, and that's completely like
it happens that so keep in mind it's in a prime field, right? So it's a modulo can be a prime number. So you
what?
pick. It happens that if you pick the number from prime field, that to the power of 8, or in general to the power of maximum for the size of your stack trace, top to the power of 2, topped up to the power of 2, then it happens, it's just a good way of indexing, so that fast Fourier transform is more efficient than if you index it by 1, 2, 3, 4.
So the simple property of this trace polynomial is when I plug in q3, q to the power of 3, I get 3. Yeah. So that's it. That's just the interpolation.
Thank you that I could explain it. Now I understand it better.
That's good.
Yeah, it's incredibly precise, I think.
There's a lot of details that get skipped.
Yeah.
Good to feel it.
Okay. So we told that this trace needs to follow certain rules in order to be like anything sensible, anything valid. So the first rule that we can all agree on is that Q0 needs to be 1, and also Q1 needs to be 1, right? That's always what happens here. There is nothing else. Yeah. So the T of Q0 is gonna be 1. That is our first rule. I will write this over here. And in order to always have this rule satisfied, we are gonna develop right now our first boundary constraint here. And this boundary constraint I will call, because this is let's say our first rule, I will call B1 of x, and it's also gonna be function. I say function, not necessarily polynomial, you will understand in a minute, but I define our first boundary constraint, and I'm gonna right now write how it looks, and we're gonna explore its properties, that it's really bounding the stuff. So
sorry for stopping the presentation, but I don't understand about the roots of unity. So we need those roots of unity of the power of 2 to the n to the power of n to exist. So there should be a cycle in our field of the size of 2 to the power of n. But if it's a prime field, then its order is the number of its elements, no? Then it's prime, then it's not a power of 2. So how do we know that those roots of unity exist there and we can find them?
yeah, so we have a roots of unity, but what really happens when we plug yeah, but I didn't get exactly your question. Why is this
So
not
we need
possible
to
to
find a q,
yeah.
and q to the power of 8 is 1.
Yes.
How do we know that this q exists?
I don't know.
Okay.
It's like you have to pick. You have to. Yeah. You have to pick a field that can satisfy what you need from the algorithms and stuff. What needs to be satisfied between all of those parts, I don't know, because I didn't explore them.
But I'm thinking that what field needs to satisfy is that it should have a cycle of the size to the power of n.
Yeah.
But then the order of this field is prime, and every element, if it's a a prime field, then
The order of the field is prime minus 1, I think.
prime minus 1.
Yeah, so
And
it's
that's the power of 2.
Yeah,
Okay, so we
Yeah.
need to find a prime
That's-
field that's
that's-
power of 2 plus 1.
yeah.
That's a surprise. Did you say the prime field is order of prime? The order of prime field is always prime. Do we agree on that? It's in the name.
That's not what
We
Bartek said.
don't
Bartek
agree.
said it's prime minus 1, right?
Yeah,
We don't
that's
agree
what
with
I think, but let's
The
not.
prime field, there's p elements,
Yeah,
but when you look at the multiplication group of it, you have to exclude 0. So you have one element less,
Yeah.
and that's a power of 2. Or
Okay.
like it's a multiple of a large power of 2.
yeah.
Got it.
And you can like divide this large field into the small, let's say, cosets of this sort of site.
And this minus 1, you have as many subgroups as
Divisors.
divisors. So it's kind of speaks the same way as group, group of
Yeah, we can later like talk about what is the definition of the Stark prime, and we can see about that what is the correct exact value. So we can like have a chat after that.
Yeah, okay, that's
Uh,
all very helpful.
So our first boundary constraint is gonna look like this: that we've got a numerator and denominator part, and in the numerator part we are gonna define what rule needs to be satisfied, and on the bottom part we are gonna define where this rule needs to hold. So what and where needs to hold. So we say that t of x needs to equal 1, and this property needs to hold in the place q equals x equal q0. So we say x equal q0. So we say what t of x needs to equal 1, but when x is equal to q0. We can explore this a little bit on the graphical calculator, because it's or maybe not yet. Yeah. So what is the I'm thinking about if we could like show this right now. Okay, so forget.
If x is
forget
zero,
about-
it's a division by 0.
Yeah, I'm gonna just talk about it. That's correct. But so imagine that our trace is correct. So when this is, so it's like this. When this trace is correct, I'm gonna write it here. I know that t of x is also correct, so it's in the place x equal to g0, it equals 1, so this whole top part is equal to 0. And what I can write is that t of x minus 1 is equal to, I can factor out the 0th place from this polynomial here. So I can write x minus g0, because this is the 0 place of this top numerator part, and times some q of x. I don't know what this q of x is, whatever it is. So when the trace is correct, this formula can be expressed or equivalent to this one. Whatever the q of x is, the q of x needs to be something to match this equal part, when the trace is correct. But when the trace is not correct, so not, I cannot refactor out this kind of term. So I'm gonna have the t of x minus 1 equal to some, let's say, p of x. I don't know what this p of x is. It's just the same as this. So what we can observe here, when we've got...
Why is that?
what?
Why can't you refactor?
Yes, because when I'm looking at the places when this whole polynomial zeros, I don't see a point that it zeros in the q0 place. So I can't factor out this sort of term. Maybe I can factor out other, but I don't know. But I can't factor out this one.
So
Is
the
it
one on the top, the polynomial, that is qx times x minus q to the power of 0.
Yeah.
Right? So that's like the whole polynomial that's going to describe our...
This is the equivalent representation of this sort of term when the trace is correctly defined. Is it clear? Yeah? Let's have a little bit of time. I'm gonna drink. Yeah. And when the trace is not correct, I can't factor out. Maybe I can factor out something else, but I don't know what it is. So I can't factor out the x minus g0 term. So what we see when the trace is correct, I have b1 of x, and this b1 of x is gonna look like x minus g0 qx over x minus g0, and that's gonna be just q of x. And this is the polynomial, so I know that b1 of x is right now also polynomial, because it's equal. But when it's not correct, when the trace is not correct, I've got p of x divided by some x minus g0, so it's some kind of rational function. It's not going to be polynomial because it doesn't have this term on the top, so they can't reduce. And the b1 of x is just rational function, not polynomial of low degree. That's in regarding to Frey. So when it's not, the b1 of x is equal to p of x divided by x minus g0, and this is the rational function. I can say rational, and this is the polynomial, and that's the boundary constraint that we observe that has a property. When it's met in the trace, it's polynomial of low degree, but when it's not met in the trace, it's rational function. So that's just like a switch here. That's important. That's kind of like essence. Yeah. So right now, we can explore this a little bit to see on the graphical calculator to see if we are if we intuitively see if we intuitively see what is happening here. So let's say we go to Desmos. Yeah. And we're gonna define something similar to the boundary constraint. So let's say x minus 1 on the top.
Could you maybe turn a bit to the right so people can hear you? Yeah. Maybe you can turn the whole thing.
I've got a cable here. Wait. Wait,
Would
okay.
that work?
Okay.
Maybe a bit more even?
Yeah.
Just so you
Okay,
speak to-
good.
Yeah.
That's good ideas, good ideas. I will continue defining this stuff.
Enough space?
Yes, it's enough.
Thank you.
Cool. X minus 2, and let's say x minus 3. And I'm gonna have a here, and the step is gonna be... So, when my a, so the stuff on the bottom is not reducing with some of the terms of the top, so the idea of not correct trace is happening here. I've got some function that is for sure not a polynomial here. We can intuitively see that. It's some rational function that goes to the infinity in a couple of places, and that's completely not a polynomial in any way. But when I like move this stuff, this a parameter, when it meets finally some of the term of in the top part, it's gonna reduce, and we for sure got a polynomial right now. It's just x minus 1, x minus 2, x minus 3 polynomial. So this a, so this sort of works like just turning b of x being polynomial or being rational function. So we can like explore all of the places that this becomes polynomial, and all of the places that this is not a polynomial anymore. So when I got to 3, it's also going to become a polynomial. So I hope you right now have an intuition about this formula that is becoming polynomial of low degree when the trace is met, and becoming a rational function when the trace is not met. Yeah. So this is our first boundary constraint, and what we can say that this top part is says what needs to be satisfied, and this part says where does this stuff needs to be satisfied. That's it. Yeah. So this is our first rule. Our second rule is really similar. This is just tg1 is equal to 1. So we can like write the same b2 of x, just changing the g0 to g1, because only the where place is changing, not the what place is changing, but just the where place. And I can define right now the boundary constraint that like fits both of these rules inside one. So I've got b of x that is like a total, let's say, and it's gonna be tx minus some. I don't want to use p. Let's use a of x. I will define a of x in a second, and it's gonna be. It needs to hold in two places right now. So x minus g0 place, and also needs to hold in x minus g1 place when the a of x is defined like this. So a of g0 is 1 and a of g1 is 1. So I defined, let's say, intermediate polynomial that just holds me this data for the g0 and g1 place, and this part is telling what needs to be satisfied, and this part tells where does this boundary constraint needs to hold. Is that clear, or it was like too big step?
Sure, stupid question, but you have said intermediate polynomial.
Yeah.
Would you
The a of x I defined.
What doesn't change?
Can you rephrase the question?
Intermediate, I think that there needs to be a and b. In order to
No, why a and b? I defined this a of x to hold me these two cases in the single case. That's just it. So I defined a of x in the g0 place it holds 1, and in g1 place it holds 1. And this is like the, let's say, machine that outputs me the values on the places I'm interested in. So that's only this. It's like intermediary. I can, when this polynomial is 1 in both places, I can like say, okay, let's go with 1. It's also the same here.
I think it's intermediate.
Yeah.
So it includes two gates, but
Yeah.
not all of the gates, so we accumulate.
Yeah,
gates.
yeah. This when I write -1, forget about ax. It's just the same. It's just holding me these values, just let's say dummy polynomial. But I want to have this nice looking, but forget about nice looking. Yeah. Any questions?
I wanted to ask if Q is the same as G. We were talking about
Q.
and then switch to G, but I don't think there was a
Wait.
definition of
Q is the same as G.
These Q's or these G's on the left? I think
This is Q's. All of that
Yeah,
is.
but you were saying G when you were explaining.
Oh shit. Okay. So it's all Q's. Sorry about that. Sorry about that. G. It was similar to G. So the Q's, the roots of unity. So this stuff is our total boundary constraint right now. That is polynomial of low degree if these two places are correct, and is a rational function of whatever formula when this trace is not following that rule.
Does it make sense to talk about degree of a rational function? Because it is also kind of a low degree. But there are like two types
wait.
of degrees. Or does it not matter here at all?
I don't think so. Yeah. We can like say that some rational function that is, let's say, arbitrary formula is the polynomial of infinite degree, right? Because you could like interpolate this, and you will always gonna like not meet. Yeah. So it's like when there is rational function, you can say, okay, I'm speaking about polynomial about infinite degree, so for sure it's not low degree. Yeah. So that's a good stuff here. Okay. Okay, let's go to the best part right now. So the transition constraint. So it's gonna constrain the whole stuff to the bottom at once. We're gonna see how to do that. Oh, wait. And we're gonna see how to do that. So let's focus on this frame only. So these three values. What is the rule to constrain them? That's quite simple. We can say that T G2, let's write it over here because Q2, sorry, is gonna equal to the T Q1 plus tq0. I'm sorry about that. So it's simple rule, right? So this plus this is equal to this. That's this what this formula is saying. But what I want also is I can just move this frame one step to the bottom, and it also needs to hold. So I can parameterize this sort of rule to have this x inside here, and this x is going to be q0. When it's going to be q0, we are talking about this frame. When it's q1, we are talking about the frame below. And we can go to up to q5, so we are going to talk about this frame here. Right. We can rewrite this formula a little bit more convenient way. Tx q2 minus tx q1 minus tx q0 equals 0. That's the same stuff. I'm gonna right now switch the table, switch the paper.
So x.
Yeah, please questions. Sorry.
Q or q squared or q cubed or to the fourth or to the fifth, but not to the sixth.
Yeah, because we are gonna right now talk about this frame that doesn't have the last value, and that's not a constraint we need to follow, right?
In general, what would be the form of our constraint? Because Fibonacci's are nice because they're a linear recurrential equation with just two terms behind.
Exactly.
And can we go any other amount of terms behind? Can we just jump
Yes.
around in this place?
Yes, we can do this sort of stuff, but we will talk about this more when we go to the provable CPU architecture, because right now we develop the idea and intuition, but this sort of stuff
you
are.
Think about the sizes of those polynomials. Here
Okay.
we just have two terms, but
Yeah.
we have like n terms. Can we have n terms? Is it already?
In general, we are gonna have polynomials that are probably not bigger than degree of 2, and I will explain you how it's possible in the provable CPU, because it's also nice. Because they're gonna be like polynomials with periodicity and offset and stuff we're gonna say about.
And does it make sense to ask why you have chosen first three elements of the Fibonacci?
First three?
Or just you have chosen first
Yeah.
three elements.
Yeah. So to develop this formula, like in the easy way, but then I parameterize this formula with x, so I can move this frame wherever I want. Yeah. We will see how to create right now transition constraints that's gonna constrain this rule, but in many places. Yeah. It's gonna be the same as this. So.
To be clear, this is specific to the maths problem that we are trying to prove. Like this is arbitrary that this be 3, right? For something else in Fibonacci, it would be a different.
Yeah. So that's just the intuition, and let's say what stuff we are working with here.
One concrete example would be
Yes, thank you for that.
polynomial
Let's put it on the table. Okay.
Some people will be able to see some of the.
Yeah. Maybe I can put it a little bit higher. We can lower down. Yeah. Let's go. Okay. Cool. Right. So that's good that we have stuff here. So right now, the transition constraints for this trace, we're gonna express this as c of x, and this formula again has stuff that what needs to be satisfied. So this rule, what we developed in the last part, so tx q2 minus tx q1 minus tx q0. So that's the rule. So this is the question, what needs to be satisfied, and right now what places. So the places are gonna be g0 up to g5, yeah, because this frame is gonna move. So we can write this in a nice way. So we can write this I equals to 0 up to 5, and it's x minus qi. So this is the places where this stuff holds. Yeah. Any questions so far? Is this clear? Hmm?
This defines our frame that we're moving.
Yes, exactly. So defines this like fork that like goes to the bottom. So what we've got here is this C of x is gonna be polynomial of low degree when the frame holds on all of the places from 0 to 5. And it's gonna be not a low degree polynomial if any of those places are violated, or all of them, or any of, even if one, it's gonna be complete mess because it's not gonna it's not gonna reduce in some single place where it should.
Okay.
Yeah.
Now, before we were evaluating on the domain which had 8, and that's nice. It's in power of 2. We can have roots of unity, but now our domain has 5. Does it throw in anything in terms of powers of unity?
Our domain is still 8. Why does our domain is
So
5?
we're moving the frame, but it's 3, so we're moving it up to 8 minus 3,
Yeah.
so up to like 5.
Yeah.
What happens if we like move it further? Then we go out of.
Yes, we go out of the values. So this, like having this constraint that goes out of the scope of the trace is not some rule we should have, because it can be met or not met, and both of the traces are going to be valid, right? So somebody calculates this Fibonacci and let's say makes mistake on the last part, and it doesn't like have influence for that because we care about the 8th Fibonacci, not about 9th, right? So that's the intuition. Okay, C of x. We see how this works. Low degree polynomial when the trace is correct, let's say right now, but high degree polynomial or infinite degree polynomial when this stuff is not met. So we define right now the composition polynomial. The composition polynomial is going to be, like name suggests, the composition of all the rules that this trace needs to follow. So it's simple. It's h of x. This h of x has the same like letter like we mentioned in the fry in the beginning. So that's kind of connection here. So it's gonna be some beta or some alpha, let's say beta of b of x. So our like complete boundary constraint b of x, let's say beta 1 plus beta 2 of the c of x. So it's a linear combination. So if either of those is a rational function, this stuff is going to become rational function. But if both of those are polynomials, it's still a low degree polynomial, right? If any of this stuff is going to become high degree polynomial, it's going to move to the h of x.
If they're both rational functions but the same rational function, then it's 0, which is a low degree polynomial.
It depends what betas you choose.
Okay.
You can have like only positive betas, let's say, whatever. Yeah, whatever is the fix for that issue, you know. Beta are random values picked by the verifier in the protocol. So it's like field element.
Okay.
It's just it.
So betas are random, so this case is included.
Yeah, yeah. So this is the randomness supplied from the verifier, and it's important because we could have without these betas, just B plus C, but this stuff needs to be like a little bit harder for the prover to predict what this value is gonna be. So it's hard for him to develop malicious example of this h of x that is gonna just pass, you know, the checks of the verifier. So the randomness from the verifier is for the increasing like security of the verifier when it's like comes to the verifying if this function right now, we don't know if it's polynomial or not because it depends on the trace, but if this function is like low degree polynomial and goes through fry and verifies right now on the verifier side correctly, verifier can be sure about that the trace follows all the rules. So when later prover says about let's say A8 is 21 and all of the rules were satisfied, the verifier right now knows that this result is correct because it is convinced about the trace was following all the rules.
And the randomness is produced one time or multiple?
During the protocol, it's like 10 of times, like a lot of times. So there are those betas, and the randomness is produced by the Fiat-Shamir heuristics, and this is like hashing the values one after the other, and the value that comes out of this hashing of previous one is just the random value we are working with. So that's it. So it's the Fiat-Shamir heuristics to get randomness in the zkSTARKS protocol.
We're just trying to build the intuition about the names of the polynomials. We have
Yeah.
H, C, and B. Do they mean anything? Like C
No.
for constraints?
Yeah. C is constraint polynomial, B is boundary constraint polynomial, and H is composition polynomial. We can't use C because it's gonna confuse. So yeah, that's it. Yeah, so that's part of the math. And also, right now, I can talk a little bit more about. So this guy goes to Fry right now, right? And it's gonna be verified on the verifier side. But there is like a lot of stuff that needs to happen after that on the prover side, because the malicious prover could like put not necessarily the H defined this way into the Fry. He could like put x minus 1 into the Fry and send this to verifier. Verifier is gonna be happy, but nothing like sensible was proven here. So the verifier is gonna prompt prover, okay, give me evaluation of this h of x in couple of places or in single place, or it's gonna be h of z, and z is gonna be out of domain value here, whatever it is, but it's gonna be the value arbitrarily chosen by the verifier, so it's gonna get it's gonna get knowledge if the prover really is putting this h of x into the Fry or not. So it's a couple of steps in the. We're not gonna go through them because they're kind of harder, but the prover needs to do some little bit more stuff to convince really the verifier that it's not doing any malicious stuff here. Yeah.
Is pairing involved in that?
No. There is no pairing involved in that, only the next Fry, because they're gonna be defined the deep composition polynomial, and what is the deep polynomial, sorry, and the deep polynomial is the short for the domain extension for eliminating pretenders, and the pretender could be the prover, and it's gonna the action of that is gonna be targeted to eliminate a pretendative, let's say, prover, or whatever is this word, but to eliminate the prover that could put something different to the Fries and be like inconsistent. And this deep polynomial is gonna be like something that we choose another value, and we with some randomness gonna check if these two values, random values, also with the randomness in the formula, is gonna hold some certain properties of these two, let's say z or like x0 and z. That's gonna be this. But this step is for it's gonna be super hard for prover to come up with the scenario that when the verifier is randomly choosing some points, and verifier is checking if those 2 points are holding some certain property between them, and it's gonna be super hard for the prover to just prepare this scenario because it's random choosing.
On very high level, what is the property we're talking about?
It's like evaluation of the deep polynomial at certain point, and that's gonna be like it should meet the expected value that the verifier expects. So it's gonna be
The quotient polynomial is involved then.
quotient.
Like
That's
again,
kind of the C, right?
the
Can you
reminder
can
polynomial, right? Involved then, right?
no, why?
Okay. Well, I'm just trying to guess what's the.
Yeah, I can show you the deep polynomial in a minute. It's a little bit larger, but still the same, let's say, concept, but it's constraining, the values that were needed by verifier to calculate h of x evaluation on its side. So that's it. But what?
You don't have LP curves at all, so there's no
Yeah.
pairing.
Yeah.
It's hash-based, right?
Yeah. The pairing stuff is on the SNARKS side totally, not on the zkSTARKS side. Yeah.
Which side is the dark side?
Both.
to be
The other one. The other one.
to be honest,
So
Huh?
did you say that the prover runs the fry check
no, it's running the fry prove part.
and the verifier
It's
runs
running the fry
Oh.
verify part. Right.
So that's what the verification is, right? And that is
Pretty
fast.
pretty much.
The
Yeah,
fry
it's
check that is fast, right?
yeah. So like I told in the beginning, the intuition about fry could be like having the interpolation, like regular, and sending then all the values. Okay, verifier, let's go and you can interpolate this data, and you should have polynomial of low degree. But this is too much to handle. This is too much to send. It's gonna be, let's say not terabytes, but gigabytes of data of the proof. So that's gonna huge. But this fry is just a commitment of this sort, and it's really like lowering down the amount of data and also lowering down the amount of time complexity because it's huge.
And it's based on hashing, right?
Yes, it's based on hashing. Later there is some folding introduced, so this whole stuff is lowering down in size, and let's say this whole evaluations of the polynomial can be lowered down to the single value that is really like meaningful right now, and it's gonna be sent to the and it's gonna be so the verifier on the verifier side is gonna go also through this folding scheme, but the prover is gonna supply him only the needed values to go through the folding on each side, not the whole other parts. But also the verifier gives here the randomness, so it's gonna be super hard for the prover to come up with the scenario that meets the stuff. It's lots of to talk, but that's what I want to tell you in the beginning. So this hopefully give you the sense why the zkSTARKS has the leverage they have. So I can verify somebody's computation really quickly by, let's say, verifying trivial concepts here, and this is giving me the leverage. So that's the key of this presentation. So why does this leverage exist? Yeah.
So the verifier can ask the prover to verify H at a random point.
Yeah.
The honest prover will choose this B and C polynomials and combine them in a linear fashion, but
Yeah.
the dishonest prover can do whatever.
Yes.
And the C polynomial is public to the verifier, but the B polynomial is private.
The set of rules is public for both sides. So the verifier side knows what rules to expect to be met, and also the prover knows.
Rules are in the C. In the B we have the values. So B should
Yes,
be
but
private.
boundary constraints are also the like public rules that need to be met right here, right? It is the first two ones is the stuff we agreed on that needs to be
Got it.
needs to be met on this trace.
Yeah, because the B and C is basically the code, the
Yeah,
function,
yeah.
right?
Yeah.
So how do we get to B from C again?
Can you again?
How do we get B from
B.
C?
No, we don't get B from C.
What's
There-
the relationship?
Okay, so the B is talking about the constant values, let's say, in the trace, and the C is talking about the intermediary, like intermediary values that, yeah.
Where is the trace? We don't see the trace in the math.
Yeah, which one is the trace? The B then?
No, the
B
trace is
is
over
code.
here. The trace is over here in those formulas. So
X and
yeah,
CFX.
yeah.
So the first 1 and 1 are kind of our public inputs, but then 2, 3, 5
Yeah.
are kind of our private inputs, and we didn't have them.
I wouldn't like split this trace into the public and private. The whole stuff is, let's say, public because those were the rules we like constrain on the verifier and prover knows. The stuff about private input is not really here in this example. So it's so the private input would be the trace that is not constrained by the boundary polynomial, by the boundary constraint, because it's whatever somebody puts. But later after that, there are going to be transition constraints on this, let's say, yeah? Yeah, so these boundary constraints are like public inputs, not...
So the public inputs and the code is indistinguishable in the polynomials.
Indistinguishable, why?
Because public input is basically boundary constraint.
Yes, so this stuff is gonna always be the same, nothing is gonna change. There is no private input that's gonna alter this trace. There is like fixed example, that's it. Yeah?
Maybe what Leon meant is that if this was a Fibonacci sequence for big number,
Yeah.
then all of the numbers in between in the execution trace would be kind of private from the verifier, right? Is
No,
that
because
what you mean?
Yeah. Okay. That's
That they
true.
don't need to know it,
Yes,
but
yes,
also they
the-
can't know it.
Yeah, what
From
the verifier is gonna know from this whole trace is just the value that it cares, and the proof that the constraints were met. All, yeah. So
does
that's
it learn the value? I thought it only learns that it's a correct value, and it does not learn the value itself.
It learns
No.
that the polynomial is of the low degree, basically.
Exactly.
so once again, the verifier. Yeah, exactly. This is the output of the computation. We care about that. The verifier should know this to, let's say, go forward with some process, right? This is the intentional. So
Except if you want the verifier to learn about the final value,
Yeah.
the verifier has to mention it in a boundary constraint.
But then
So like
there's no zero
the
knowledge.
example that you have here only talks about the fact that we have two ones on the input, and then we have a trace table that is according to some rule.
yeah,
But there is nothing that the verifier does specifically to learn that the final value is 21. So if the verifier wants to ensure that the final value is 21, you also need a boundary constraint for that.
yeah. So sending this value is a little bit more complex than just, let's say, let's say the prover is gonna output to the to the verifier. Okay, I've got in the Q7, I've got this. You won't like believe in that. You have to have a proof. Inside the proof, you have to boundary constraint, like you said this. But once again, the verifier is gonna know this value with the protocol, but and is gonna know this value, and also is gonna know that the whole every rule that they both agreed on was met.
But then there is no zero knowledge here, if the verifier knows.
Yeah, in this in this exact example, there is no zero knowledge because there is no private input, right? We have this trace that is completely fixed every time the same, and the verifier knows the last value. But when we want, like we mentioned before, when we want some private input, the example is going to be a little bit more complex, and it's not going to boundary constrain this private input. And that's when
I would
this.
argue that it's enough to remove the B polynomials to get zero knowledge.
Yeah,
Because
yeah,
then you would have some
yeah.
starting point
But
and
it's not going to be
above,
Fibonacci right
and
now,
you-
right?
But you get to a point what was kind of calculated like
Yeah, exactly.
Fibonacci
So.
number,
Mhm.
but you don't know what it started with.
It is a bit weaker than zero knowledge though. So like it's almost correct, except we cannot say that it is technically zero knowledge because the verifier technically could learn something about the first two inputs. So it's not necessarily zero knowledge, it's
But
just
because of brute forcing or reversing calculation,
Yeah,
or for
exactly.
some other reason.
exactly.
Yeah, yeah,
Like the
yeah,
verifier
yeah.
technically could reverse some portion of the
Yes,
verification
yes,
to
yes.
learn something.
But
so
it's-
not
but-
technically zero knowledge.
Yeah, but it's a lot of effort from its side, and what we like aiming to pass to you here is that this calculation this output can be trusted. Yeah, so it's like really hard math to do something, and let's say big I don't know some
But the constraints are
average.
met, basically.
yeah. So I get a output that was really hard burden to calculate, but I also get a proof that this was calculated correctly with.
But the verifier could reverse engineer only a part of message input. Some random part.
It's I think it's quite open. Like we don't really know what the proper like if you don't take some additional steps to make this fully zero knowledge, then we don't really know what the verifier can like it's just an open hypothesis. So how much knowledge can you extract out of a proof that doesn't do any blinding?
Yeah, let's
And
yeah.
I have one more question.
Mhm.
Could you repeat for dumb people,
Mhm.
for me, where is trace polynomial here? Because I don't know.
So this C of x is this, right? And in this C of x, we've got a trace polynomial rule that needs to be satisfied on those places, and that's where you've got your trace polynomial. And the same on the boundary constraint. You've got a trace polynomial that needs to be 1 in those two places, so that's where your trace polynomial lies, pretty much. Yeah, we can like expand this formula, but it's gonna be
Like in
big.
all zero knowledge, you turn trace into polynomials, basically, and then you do the calc.
No, in long you turn simple valuation, not track.
Okay, so right now the
Sure that we learn more than the 50%? So are we sure that we learn more than we can deduce from the constraints?
I mean, so like, yeah, like the example is kind of silly, right? Because the computation here is reversible, so it doesn't matter.
Yeah.
Like I can learn what the inputs were.
yeah,
But
exactly.
if this was, for example, like if this was encoding a hash function, then it's a more interesting question. Then, right?
Yeah, exactly.
Like if I know the output of the hash, I still don't know the input. And then it's unknown whether or not this version of Starks doesn't reveal anything about the preimage.
It heavily depends on the program, right?
Exactly, exactly. This kind of stuff is pretty dummy because when we like get something more complex, it's gonna be like 10 of those papers. So
Yeah, but the example allows all
yeah,
build mental model.
exactly. That's what I tried
And
to
it's
develop.
very good.
Yeah. And we've got a program that is completely, let's say, open, and we know what happens inside this program because it's what this is, but what we can easily expand this stuff. So yeah, right now, like we mentioned, we've got dummy Fibonacci, but right now we want to explore what needs to be done to have a provable CPU. So we had certain rules here, let's say 3 of those. That was simple. But right now, our trace is a little bit more developed. So our trace has 6 columns, and right now, let's say it has only 16 rows. And this trace is essentially the same, only the values there. But there are much, let's say, bigger set of rules that needs to be happening here. So let's say, for example, I'm like thinking about dynamically here about this example. Let's say this cell needs to be plus, let's say this cell needs to equal to the, let's say, result cell in every iteration of this CPU, or like every 6 iteration, or like whatever.
So these are a bigger frame that we move.
Yes, exactly. So
Or 16 by 16?
no, it's like 6 by 16 frame, and this is the single clock cycle of CPU. And when the second clock cycle comes, we've got the same matrix on the bottom, added to the bottom, right? So imagine if, let's say, if we've got some rule, whatever it is, we've got some rule that these two, let's say, this three cells needs to be like this plus this needs to be this. So we are gonna experience right now that when we say something like this, that txg2 and this x is gonna be the parameter the same. This is like the same q0, q1, q and something. So we are gonna experience right now the periodicity of the rule. How? So we say that this stuff needs to be constrained in this way, but not this stuff. So the x1 below, right? We say that this stuff needs to hold, but on the next clock cycle, so over here on the 16th row. So this is gonna be a period of 16, right? Offset 0 because it's first. When it's like here and here, let's say, it's gonna be offset of 4, 5, and it's gonna be periodicity 16 also.
This 16, does it depend on our program, or is
No, it's always the same because this is the definition of CPU. This CPU have flags, have instructions, have operations, have like, let's say, let's multiply, let's add, let's move the value from the memory, let's whatever, yeah.
And each row is one instruction, isn't it?
And what?
Each row is one instruction, I'm guessing.
Each
Kind of
row?
like
No.
clever.
No. It's not that simple. This CPU in this frame, in this clock cycle, is gonna do one thing, let's say. So it's gonna, in this clock cycle, it's just gonna, let's say, get OP0, get OP1, multiply, and save this to the res, whatever. It
So
is the
what
OP.
I meant is each row represents kind of like one instruction of the CPU, and kind of in one, but probably most is disabled.
No. this is the one snapshot of state of the CPU, right? When I look at this, yes, this is the one snapshot of what, because you can think like this when you like learned a little bit about CPUs. Okay, let's think about this to be registers, this to be like some register that hold intermediary values, and this like instructions or whatever. And this is like a snapshot. So in every clock cycle, he's gonna do one operation, or maybe let's say two if this is like well optimized or whatever, but or like more. Like normal CPUs do. So it is like one single snapshot in single clock cycle what we see here, and this CPU is constrained in many ways. It's described in the Cairo paper because it is the let's say the Cairo thinking about that. And this CPU is constrained in many ways. I will show two of them in a minute. But right now, when you've got a CPU that is constrained and you've got a list of rules, you can do exactly the same as we did here. So the CPU is going to output some output after, let's say, 10,000 clock cycles. But I also show somebody that I followed all the rules. And I've got a proof of arbitrary program right now. Do we see that? Do we get that? Yeah.
What are you trying to do there?
Where?
So there is the general architecture, and that's an example.
So this is the architecture, and this is just the detailed description of this column here. So that's only the named values. That's it. That's the named cells, so they have more context. But this mempool is the same here. So it's not aside to the CPU, it's just the description of this column. So it's not like 6 columns plus 1. It's not like this. That's just the description.
Just to have an idea, basically, one frame of that instantiated with that. So through how many frames do you cycle that?
Yeah, it depends on the because when you so when you've got a program, you compile it. You've got a memory. And you've got a set of instructions to follow for the CPU. So this determines how many times the CPU is going to clock cycle for.
So, but basically what I'm trying to understand is a bit of performance here.
Yeah.
Okay, so...
It's hard analysis, yeah.
Okay.
Yeah.
So you have not done that?
Not today.
But what do you mean about analyzing the performance? What was your question?
Well, a CPU keeps, keeps clocking.
Yes.
Okay.
Yes.
So you keep trying to prove that. So you are instantiating that mem pool at each clock, and every time you have to prove.
Yes.
And, so what is this? And you are applying the free protocol.
The fry.
The fry protocol.
Yeah.
Correct.
Yes.
So does it manage to keep up?
But you are not applying the fry protocol dynamically on every clock cycle.
Okay.
What constraints, what rules do you have? You've got hold this trace through hold the program, so it's really large right now.
Okay.
And you've got set of rules that are here, and this set of rules is applied at every, let's say, matrix of this size on every step of the CPU. So every rule has its periodicity. So how many rows I need to skip to apply this rule once again, and that's what is the place answering where this rule needs to be followed. So I've got still only this single set of rules that are periodic right now. So they are not, let's say, of this simple formula, but they are periodic and they are applied in many more places. So this stuff is enlarging when the number of clock cycles is enlarging, like this way.
Is the application of the mempool just an example, or you are applying it only at the mempool and the rest remains fixed?
I don't get the question right now. Why do you
Are you considering only the mempool, or are you?
No, I'm considering the whole 6 columns here and many constraints on this, relations between the cells. And this mempool, like I told you, this mempool is only the description of this. Of this column here, so it's detailed. I could cut out this stuff and place it over here because it's addresses and values. So yeah. That's pretty much it. And you right now have a assembly for that CPU, yeah, like every CPU have. You have right now, let's say, intermediary representation. So the assembly is called CASM, Cairo assembly. Intermediary representation is called Sierra, so safe intermediary representation. And right now you can define your language like Cairo, 0 or 1, whatever. And you've got compiler and you've got your code written in Cairo. You compile down to the instruction of this CPU. And after that you can run this program. So you've got trace only. And after that, this trace can be put into the prover. So it's like evaluated if all of the constraints were met. And you've got a proof after that. And goes to the verifier.
How about the performance of, let's say,
I will show you the live demo.
okay.
It's going to be on a Fibonacci 10, but it's going to be in the language of Cairo. So it's not going to be this example, but it's going to be in the instructions of the processor. It's going to be bigger. But the performance is hard to tell. It depends on everything. It depends on the layout you choose, so the amount of built-ins you choose. It's dependent on many stuff. Because this CPU has right now 6 columns, but on the specific layouts, it can has more columns because it's needed to have, let's say, lookup tables and stuff. And also it's gonna be, yeah, so it can be bigger, smaller, and whatever. So it depends on everything, literally.
So the schedule represents the whole virtual machine, basically.
Yeah. Yeah. This is the virtual machine. This is the emulated CPU. We coded and.
And as a sanity check, can we, let's say, do addition of 2 numbers and getting something into memory? And
Yeah.
okay.
Yeah. You can multiply whatever we want.
So we didn't talk about the architecture exactly what this all means, but if I understand it right from what we already discussed, it has
Yeah.
some kind of registers. We can load registers,
Yeah.
we can unload,
Yeah.
we can do
Yeah.
some operations. So
Yeah.
it's similar
Not
to
many,
modern
not
CPU.
necessarily as many the registers. I think there are like 3, but I don't know.
Okay.
So yeah.
But we can think about it as a modern CPU,
Yeah.
and there we think about like flows of instructions and instruction starvation, like do we have enough data,
Yeah.
what are bottlenecks. So what I'm thinking here, can we have like double core CPU? Can we have more than 16 but like 20 rows, and then we don't starve on reading data, for example? Does it make sense?
But
Can
then,
we like add a core to the CPU?
then we need parallel world.
I think it's possible, but I don't know if somebody already tried that, and the performance like problem is much bigger because when you add single column, the much more math needs to happen. Every column is really expensive to add.
I'm
So
talking about adding rows here.
okay, adding rows. So it's like completely copied, but on the bottom one single. That's it.
I will need to look exactly into how this architecture
Yes,
works.
that's why it's hard to tell about
Yeah,
this.
but I guess like there are just
Oh,
couple of
sorry.
places where arithmetics can happen, and other places are just like reading, writing.
Yeah, so you can, like in every CPU, you can have multiple operations in single clock cycle. That's, I think, what you are talking about. Is it right?
Yes. Yeah.
Yeah. So yeah, if you are clever enough to like do this kind of stuff and following also all the constraints and stuff. So yeah.
So let's say, for example, here we can do I don't know 2 additions, 1 multiplication.
Yeah.
But then if we want to do some matrix stuff, we want to have SIMD instructions, and for SIMD instructions we want to have like 4 at the same time,
Mhm.
but they're on the same values, so they're already read into the registers.
Yeah, yeah. So you are talking about the really like practical problems and optimizations on terms of like maybe even assembly to like write and stuff. I am not expert enough to tell you about this kind
I'm
of.
just thinking like, is this at all the area that can be configured, or this is the CPU and we're working with this?
I think this is the CPU we are working with, and we are, let's say, bounded to how it works, because changing the CPU is gonna change really lots of the stuff. It's gonna change the constraints, and also it's gonna be like settled on both of the prover and verifier, so there is like gonna be compatibility issues.
So
And
if we can change the CPU, then we can have ASICs on STARKS.
yeah, so you can, it's not,
RISC-V is doing more or less.
yes, exactly. The RISC-V is not designing its own CPU, it's just using the RISC-V, so reduced instruction CPU, and they are defined probably the whole lot number of constraints to constrain the CPU and just do the same. But
I believe they're using STARKS.
yes, they are using STARKS. Yeah. The RISC-0 project is using STARKS for sure.
And
Mm.
CPU has to be the same on the prover and verifier. Right?
No, only the prover side has to have, let's say, instantiation of the CPU and create a trace, but the verifier only has to have knowledge what sort of constraints needs to be satisfied on this trace. So the prover is doing the calculations and literally the addition and multiplication or whatever the function the processor is doing, but the verifier side is only like interested in checking if all of the rules defined for this CPU were met. So it's not emulating CPU on its side, because it would be like doing the calculation again on the verifier side, so there would be like no point in any of that.
You rephrased the question. Has this 16 number ever changed in the history of Starks?
I don't know, maybe in some early versions, I don't.
So this is not something they upgrade with every hard core.
I think it's hard to upgrade such things, yeah, because yeah, it's problematic, let's say. I think they developed the stuff and they've got like lots of places unused, you can see, and this is probably the backdoor for improvement, but I don't know. I don't really.
Backdoor for improvement.
Yeah, so I don't really like know history of that and stuff. So yeah, so we can explore really quickly, I think. Let's say one of the constraints that is on this CPU. I'm gonna have another example in a minute. So in the CPU there exists like 3 registers. There is AP, so allocation pointer, so the next place in the memory that can be allocated. There is FP, that is frame pointer, and this is the like implementation of the frame of the function, so it's like the stack. And also there is like PC, so it's program counter, and that's, let's say, 3 registers that are in this CPU. And let's say how to read this simple constraint. So next FP, so the FP in the next clock cycle is just gonna be either DST, whatever it is DST, but when this F flag is 1, it's gonna be DST. When the opcode call flag is 1, the next FP is gonna be A plus 2. But if either of those flag is not put into the 1 value, it's gonna be the old FP. So the next FP is not gonna be changed it's gonna be the old value. So we either have the next FP equal to FP when no flags. Either is gonna be DST when the opcode read is is put up, and either it's gonna be opcode call AP plus 2. So
DST is pre-calculated value, and what could be AP?
AP is just gonna be the integer of allocation pointer. So let's say it's just right now 104, and it's gonna be 106 for the next FP. So
It's like a code pointer.
it's like the next. It's like the next place in the memory that can be written to. Yeah, so that's allocation pointer, and this stuff is this constraint is implemented in over here, and you can I put a little bit of code here, so we are talking about real stuff, and this is coded. This stuff is from the Platinum prover, from the Lambda class. So yeah.
How does this think model memory? Like,
Huh?
how does this think model memory? So you said you talked about the CPU and the CPU has a fixed number of registers, but now memory can grow larger. So how do you embed it into the constraint?
So you've got apart from the constraints of the CPU, you've got a constraint from the memory. So let's say there is a constraint for the memory to be continuous, or like there is a constraint for the memory to be like increasing in addresses or something, and there's like a whole lot of constraints on the memory side to be like valid, right? So more of this stuff can be read in the Cairo paper. It's hard to like jump back.
Put things in the memory and get things from the memory that might be many frames away from each other, right? So how do you?
I think so.
And then do you have like a constraint cross frames, or
I think you don't have to constrain that if you have assurance that this memory is continuous and other stuff. I don't want to like drive on talk about this because I'm not really super familiar, but more of this stuff can be read on the Cairo paper, and it's completely clear. That I don't remember the whole Cairo paper right now.
And I guess here we don't care about the case when both are true, because they cannot be true,
Yes, because either you return from the call function or either you call another function. And this is also needs to be constrained because you maybe malicious prover is gonna set this, right? So this needs to be as like constrained in other place. Next thing is just a next AP. AP, it can be like, next AP can be AP plus res or AP plus 1 or AP plus 2. That's it. So that's also defined over here in the Platinum prover. So yeah, that's how it works. That's how we constrain pretty much this whole CPU with the.
Code is actually every constraint is like a dozen of lines.
Yes, yes.
Building
So
the polynomial from scratch.
exactly. So this polynomial is written here, and the minus next AP is moved to the right side. So this res should be 0 when all of this stuff is met. Yeah, so that's it, and it's evaluated on the whole domain, and later it's generated the composition polynomial, and it's checked if it's really low degree.
Do we have an understanding of how big is the constant in the system? So if we would like to compute those like 8 Fibonacci numbers, then the sizes of the polynomials will be 8 multiplied by.
I don't know.
Okay.
Yeah, because I don't know how well this stuff is optimized. So maybe every step of this Fibonacci is gonna be one single clock cycle of this whole CPU. Maybe not. I don't really know. But yeah. But it has, of course, large overhead. Yeah. Yes. So also I want to talk a little briefly and quickly about recent news in zkSTARKS technology. There is an update on the Stone prover to version 5, and this update is introducing the Poseidon hash function, and because recently, before that update, we had really trouble with, you can choose like hash function for the for either friendliness for prover, so the regular CPU like x86, and you can choose friendliness for the CPU of this architecture. And it's like always the fighting between each other. So either have fast proving or either has fast verifying. And when you've got a Poseidon hash, it's like good for both, fortunately. So it's like reduced. On my exact example, it reduced proving from 12 hours to 2. But this was large program. This was like program of verifying previous proof, so it was recursive. So yeah. So.
Do you know on which chain? There is any chain that Poseidon works already, or
Chain? Oh.
That's unrelated. It's just
Yeah.
inner workings of
This stuff can work off-chain completely. It's not any chain. You can do this on Starknet. The Starknet does that, but yeah, it's like just doing the proving and verifying stuff, and that's how this blockchain is constructed. But this stuff can work completely off-chain. It's just a technology to go.
The notion of the L3 that Ethereum came up recently. 6 months
Yeah,
ago.
yeah.
So they got Starknet got a lot of funding for the new Cairo verifier for
Yeah.
creating the L3.
To give a little bit of light, I currently work on this Cairo 1 verifier with Herodotus guys. So yeah, I'm like really into the topic. And with this Poseidon, we reduced the number of steps that this verifier is currently making.
So I don't know too much about this. So a curiosity. So you said you choose the friendliness. What is that? How
So-
do you define that?
So it's kind of intuitive. So the friendliness for the prover side is gonna be hash function that is really quick on the regular CPU I've got in this ThinkPad, let's say. So it's a x86, but it's gonna this is the hash function that is really quick on this sort of CPU, but and this is the prover friendliness.
Okay.
Yeah, because my laptop is gonna be a prover and it's gonna run this program, and that's it. But verifier friendliness is the hash function that runs quickly on the CPU we introduced beforehand, and yeah, so that's gonna be friendliness for the verifier side. Yeah, because you can have a hash function that is like doing the lot of, let's say, binary manipulations, but you can also have a hash function that is working on the elliptic curves. And those kind of hash functions are really friendly for the verifier side, but you know, the bit manipulation hash functions are good for the CPU in that laptop. So Yeah, so this is the Cairo Cairo 1 verifier is right now in the good shape, and it's like deployed on the testnet and it works. So that's the news from the let's say kitchen there. And also StarkWare introduced new recursive with Poseidon layout. That's good for recursion because you've got this Poseidon friendly hash, but in the recursive steps. So that's really helping with the recursion. And also there is like new Stark protocol called zkSTARKS that is a little bit different and is using the circle curve for doing the, I don't know, I think arithmetics or something. And there's like two projects on the GitHub. You can like there is in this project there's like prover and verifier pair.
So
for
how much is it improved compared to,
Oh,
because the paper came out, when was it, 2020, I think, the Cairo paper, right?
yes.
2020 more or less.
Yeah,
right?
yeah, yeah.
And at the beginning it was very slow.
Yeah.
So how much?
It improved significantly. Let's say we are not talking about the zkSTARKS, but on the with the regular Stark. But from my perspective, when I started a year ago, it improved really significantly from that side. So, like I told you, this simple example, 12 hours to 2 hours or something. It's making good progress so far.
And
So.
that was after Cairo 1 was already live, right?
Yes. The Poseidon is really recent. It's like, I don't know, month ago or something. So yeah, it's really recent. Yeah, so you can scan the QR code because this is the latest also project we did. Is the verifying the whole Bitcoin chain on the StarkNet. So you've got recursive proofs that are going with the blocks of the Bitcoin, and the last block, the last proof, you can really quickly verify on StarkNet, and this way you verify the whole chain to the past. That's cool. Yeah. So that's possible with the Cairo 1 verifier we did. This is the example I told you with the Poseidon. So without Poseidon, it was 12 hours to prove the last step of this recursion. Verification of this recursion, that was the last step, but with this Poseidon it's like 2 hours only. But also the proofs from the zero.
Is every 10 minutes. So
Yeah, but also the proofs from the zero sync. So this is the project that does this recursive proofs. Is also coming up every 2 hours. So yeah, the blocks are much frequent, but this stuff is aggregating, let's say, of some sort. I don't know what zero sync does. We are basing on their
12
knowledge.
confirmations.
Yeah, let's say. Yeah, whatever it is. Okay.
Stone prover.
Yeah.
What is stone prover? What
Is
stone? Is
yeah.
it like robust?
No, it's like I think one of the oldest provers. It was like it's like on the beginning we really hated him because it was really slow and not really like pleasant. But with this Poseidon update, it's like doing good job. And the stone prover is the prover created by StarkWare. There is like this code I showed you was from the Platinum. It was created by Lambda class. You can create your own prover if you know the stuff. So that's completely up to you. It's not something that is closed source in any way.
So there are some open source provers, but
Yeah.
the best prover is closed source.
No, all of them is open source.
Open source now.
Yeah, but StarkWare or Lambda class, there are companies that maintain them and stuff.
Two competitive provers.
Yeah.
And STWO.
This is the new prover on the zkSTARKS paper, let's say, and this is also the StarkWare prover that is currently under development. But right now, like a week ago, I checked what is done already on this prover because it starts from the ground up. And this was like simple Fibonacci done, not really right now. I don't know if it's right now completely usable. I don't think so. It's like open source project that is starting, so it's under development. But this zkSTARKS claim to be much faster than the regular Starks, but yeah, same security. Okay, and also if you want to read further, there is Stark 101. So it explains the next steps, what happens after that, fry steps and a couple more. And also I will try to, when the video comes up, I will try to put a lot of the links in the description to read about Cairo and the CPU architecture. because it's not really simple stuff. Yeah, so some curious mind can like gain a lot of knowledge here. And that's it, I think. Let's wrap it up. Thank you. Yeah.